Hello. Today's webinar is about the CAD import toolbox for MapleSim. We have very recently, MapleSim 2015.2, and we're very excited about the CAD import toolbox for MapleSim, which is one of the major features of this release. Before I get to the presentation today, which I will go through building a model in MapleSim, I wanted to point out that there are already material on our website for your review and more information that you can find on our website. If you navigate to our main page and go to MapleSim, you will find a link to demos and videos, and also model gallery. Under demos and videos, see all sort of videos describing different aspects of MapleSim, including one specific to the CAD import. It's a short video that also takes you through the process of starting from a CAD model and ending at a multi-domain dynamic model. So it's also a good source to look at. Additional to that, if you navigate to our model gallery, where we post models that are free to download on different topics, the last 4 currently on top of the list are all based on models that are created with CAD import tool. For people who have access to MapleSim, they can download these models and have a look at them, run them. Of course, without CAD Toolbox, you won't be able to change interact with the CAD, but you still can interact with models, simulate it, and investigate its behavior. So it's also a good source of for further investigation. Okay, let's jump right into it. So I'm going to open MapleSim. So this is MapleSim 2015.2. The graphic user interface is similar to what we saw in point 1. Under the file menu, we have a new import CAD option. By clicking on it, a menu opens, and you have option to select a variety of different file formats from SAT files to Inventor, CATIA, NX, Pro-E, or SolidWorks, or even STEP and IGS or SAT files, as I mentioned. So there's an STL files. There's a variety of files that you can try with this import tool to bring into MapleSim. Here we use a SolidWorks assembly file. So I have the files of parts and assemblies in a folder. I'm going to select the assembly file in there. By doing that, the import CAD window opens, where the process of converting to geometry starts, and we get a list of all the components that are in the CAD. Here we see the representation of the model in 3D. And on the left-hand side, we see the tree as the CAD designer has created the model. So this import tool, it became apparent to us that the process of coming from a CAD design to a dynamic model in MapleSim would require an intermediate step where you need to arrange the model, potentially select components in it, and also group them. A detailed CAD model could have many small pieces in it, which will not contribute to a dynamic simulation aside from their mass and inertia. And there are things that you might just don't want to model at the system level to begin with. For example, here we have a finger gripper. You see that the 2 fingers that actuate through a equal length 4-bar linkage, which makes them move in a parallel fashion. If I look at it from the top view and turn off the perspective, I have 2 identical systems. In this case, I am going to remove one side by deleting them. So I'm only going to focus on one side of the model. And so looking at the object tree has updated. What happens when I import this file into MapleSim is that all top-level objects will become one component, basically one rigid body with mass and inertia for MapleSim. I still have some work to do because there are some components that are need to be grouped. We have here the finger gripper, so I'll just hide all others to see what that grouping coming from CAD is, whether I want to use it as is or I need to change it. Okay, so this is one rigid body. I'm going to keep that as is. Look at the other component. Turn off the finger gripper so that I looked at only this component. This is part of the base for the model that excuse me, we will be creating. So let's activate a few more components. So all of these components are all, we're not modeling them dynamically, we're just going to be keeping them for the geometry, and potentially if we attach this gripper on a dynamic system for their mass and inertia. So I'll add these by dragging them to the base, and also this one, and also this one. So now I have two of my components ready. I'll turn that off and turn the rest on. So now, as far as a rigid body model is concerned, these configuration will constitute two rigid links. So I have one here, select it, create a new assembly, or call it simply link 1, and select the other and make that also an assembly called link 2. Now I'm almost ready. Let's make everything visible. So now the parts that we have selected, they are grouped into 4 objects, and when I import this component into MapleSim, I will get 4 rigid bodies. So that's the grouping, selecting the model. Things to remember here is there are some options in preparing the model. Any component you can have the color of it changed, and you can turn to translucent or transparent if you want at this level before importing into MapleSim. After import to MapleSim, you can also access each part individually or each group individually and make changes as needed. So the next step in producing a dynamic model is to create joints. And as I mentioned, that this is a 4-bar linkage. We won't be adding joints in this window, but we will be creating the frames where joints are connected. So it's very important that we have a easy way of interacting with the CAD, and that's where the feature detect function of the import tool comes into play. By clicking on this button, it's where we add coordinates, which then translates into MapleSim as a rigid body frame. The process will look at the CAD and identifies the surfaces, any lines in the model, and also any circular arc. I'm going to start with adding a coordinate to this base frame, and after creating the base frame, it's worth noticing that each coordinate will come with a z-axis, x and y, and orientation that are taken from the surface or object that is attached to. I'm going to change the name to ground, so when I'm in MapleSim, I can use these names to quickly reference where the model, where the ports are and what port I need to connect different things to. Now I want to add an external force, let's say in the middle of the finger. So I'm going to add another to this circular hole in here, seems like a good place. And I also rename this to force. So I have now 2 coordinates added for my external connections to the system that I'm bringing in. Now I need to take care of the joints or the constraint that will be added in MapleSim to make the mechanism work. So looking at this 4-bar, we have the base and the tool link, and the third, which is the finger. So I need to include positions on this CAD object that signify the axis of the revolution of each revolute joint. So if I add one here, as far as the rigid body is concerned, that's a axis of for the one of the revolutes. I can add another one to one of the circles on the other side. So these two coordinates currently belong to the link 1 and link 2 objects. Let's give them a name that we can find easier. So I'll call this simply A, and I call this B. You can see them on the tree as I make changes. So I want so for creating a joint in MapleSim, obviously, especially if you have had interactions with the software, there are two multibody frames and a component that sits in between. In this case, we will use a revolute joint. So I need another coordinate. The best way to create the second coordinate is to just copy this coordinate and paste it on the corresponding body that will be the mating part. So I'll paste it on this body here. So that's got added here. And for this one, I copy it and also add it here. And they are exactly in the same position, which is perfect for creating the joint later on in the MapleSim, as we do normally with bodies and objects. We're not done yet. There are 2 more joints and 4 more coordinates to be added. On the other side of the 2 links, I'll add 2 more. Let's rename them as well. I select this one, call it C, and select this one, call it D. These 2 on one side are on the links, but on the other side they are on the base. So the same procedure. Any part from the base would do because it's one rigid body. So I'll copy this and paste it here as well. So now my base has 3 coordinates. One was ground, and C and D for these 2. So now we are ready to export the CAD and make it rigid body components in MapleSim. You can configure or change the view the way you want, because in the process of creating the MapleSim components, we will take pictures on the current view, and that will be a very important feature to give you to help you find out your components. This particular model has only 4 parts, but you can imagine for bigger ones, having visual cues to quickly, in a block diagram approach, being able to find your components is very useful. Before doing that, I want to also comment on the other things that are important at this stage, and that is the material properties. In some cases, the CAD comes with material properties, sometimes it doesn't. In this case, as we see that it is an alloy for that part with the density, which gets converted to the mass of this point, and of course the inertia for it. For example, this other component is silicon rubber, which is a lot lighter. So by hitting the accept and return, the components, MapleSim components for each rigid body is created, and they are added to the definition section within a hierarchy, which makes it easier to find your group of models if you have multiple CAD imported in the same model. So we get a pop-up that tells us that the model was imported, the import process was finished, and under the definitions tab, under the hierarchy, there's a new hierarchy created, inside which we find the components that belong to the grouping that we just did in our import window. As you remember, we had 4 parts, so we get the 4 parts here, and we also get a group of them for convenience, if you want to create a model and you would be using all of them, that might be a place to start, as we will start here. So let me bring on the 3D view so that as we build this model, we can also track the construct view of the multibody. So I'll just pin it to a screen so it just remains on top, and I will drag the group onto the canvas. So group is a subsystem, and as we are looking at it, I can zoom into the construct view and have a look at different parts. So the component, if I just turn off the CAD view, I can see what actually is inside. This spherical visualization are where the mass and inertia is located, and the cylinders are the rigid body transforms or rigid body frames that enable different coordinates or frames that we just added in our import window. So let's switch to full CAD view. Now that we have this system at hand, we can go ahead and start adding the components, connections together. I'll double click on the subsystem. So I have the bracket on top, and I can organize them the way I want. Let's just change the boundary a little bit and start putting them together in order. So I'll right click and say show port labels because we just added port labels, and they will come handy also to identify which multibody frame is which one we created. So we have a graphical representation on an icon. We have the naming appear for the ports on the icon. On top of that, for quick reference, if you hover over a port, a 3D representation or an axis gets visualized on your 3D construct view, which gives you quickly where is that port and what is its global orientation. So let's flip this horizontally. So I have ground. I will bring ground to the boundary of my subsystem and change its name to ground so that I can then attach to it from outside. As you remember, I'm just modeling half of my model, so the other half I'll use MapleSim to mirror. So I have D and C here. Let's see what we have on this by making the port visible on this as well. I have the force, which we added, which we will later on apply external force. B and A, do the same thing here. I have A and C on here, so I can bring this here, and I have B and D here, so we can put this here, and start adding our joints. So I'll go to the libraries, multibody, under joints and motions. I'll drag a revolute joint. Before adding our first component, actually I'll make this here. Before adding our first component, I'll again mention that by hovering over the port, we get the visualization of the axis. And as we see on the construct view, the axis of rotation is Z. So when we bring the revolute joint, it's important that it has the same orientation. It does by default. The default revolute joint axis is Z. So that was D. Connect that first then. Perfect. Now I need another one for C, and you can see as I drag and connect components, I'll attach to the similar ports. If I don't do that, you will see the components. If I connect by mistake, you will see components, they will jump. Okay. Now let's add the two remaining ones, one for A and one for B to B. So I'll connect B here, here, and do the same thing for A. Okay, so I have, I'm almost ready. Let's just close this one for now. I'm putting the force frame to the boundary as well, so I can interact with it from outside the component. Also, I'll want to use this joint as my actuator, so I'll bring that to the boundary as well and call this motor. Okay, so I have the motor here, the joint. Go outside, and I have the ground, the force, and the motor. So let's just fix this system to the ground by connecting it like this. And we will also add a actuation to the system. So there were, as people who have interacted with physical modeling or a causal modeling software in general, and with MapleSim in particular, there are a variety of options to add actuation to this model, from having an electrical actuation or a hydraulic actuations or a powertrain that actuate this through a mechanical connection. Here I'm simply going to actuate it with a position driver. So I'll go to the 1D mechanical rotational and go to under motion drivers, go to the position driver, connect that, and as a signal I'll select a ramp, which after 1 second it will take 2 seconds to reach 1 radians, and we'll set it to smooth with a smoothness factor of 0.5. Now we can run the simulation under these conditions and have a look at the results. Let's make this full screen. Turn off the primitives in MapleSim for visualizing the objects and run the simulation. So one finger moves in a direction that we want. Basically, half of the gripping action is done. So we can finish the model in MapleSim by making another copy of the model. So I'm going to copy this. Okay, now I'll need to rotate this. So I use a rigid body frame and connect it to the same base. Of course, I don't want to translate it, so I set the translation to 0, and I'll use 180 degree for rotation with respect to Z. Now we can simulate the model and see if we did the right rotation to create the second copy. Okay, here we go. Now we have actuated only one, so one side will move. By connecting the two motor ports together, we can have the same actuation move the two motors. You can imagine there could be other mechanism connecting the two actuators, like a gear system that you can use the 1D rotational components to make this model more detailed. So here we have the representation of the gripping action as it occurred in MapleSim. So at this point, we have converted our dynamic or our CAD model into a dynamic model in MapleSim, and we can perform a variety of different tasks with this model. Let's have a look at the dynamic effects that we can get from this model itself. So at this point, I'll add a probe and run the model again. I'm looking at the phi, the rotation that I'm applying to that motor, and also the torque that that motor is exerting to have the system go through the motion as described by the motion profile, in this case a smooth ramp. So if I make this side by side, here we see the smooth profile and also the changes in the torque. We have a jump in the torque in the region that we have acceleration in a positive sense, and then the negative one, the reverse of it, when we have deceleration to come to stop. So as expected, we get torque reaction on our motor that as a function of the dynamics of the system. Of course, we can add external forces to our model to incorporate other effects. So I am going to add an applied force. And I'm just adding it to one side. Of course, I can add to both sides. And the reason is that I'm going to continue this model and do a little bit more exploring of the effect that we are beginning to observe, a combination of the external force effect on the model together with the internal or the reaction for the inertial forces. So I added a global force to one of the fingers in the x-axis in the value of 1 newtons, and now I'll see an interesting result in as the torque and on the displacement. So this calls for a bit more investigation to be had, and for this kind of application, we can look a bit deeper, and that can be established by the underlying feature or the feature of MapleSim, which is being built. Having been built on top of the Maple symbolic technology. So the questions such as this, the designer wants to know, okay, I have the CAD came to simulation. The question would be, what are the effect of the external force? What is the size of the motor that I would need to be able to actuate this and make sure that the gripper applies a certain amount of force as it grips the objects, as an example that we are exploring today. So assuming the topic is what would be the torque requirement, giving the inertial forces, the acceleration that the system sees, and also the requirement for the external force. All of that combines to give me a sense of what is the motor requirement, or could be the motor together with the transmission or the gearbox that it's equipped with. So let's try to explore that in the remainder of this presentation. For that, I am going to do a little bit of parameterization of my model. So I have a force, I'll call it F, and I have a speed profile. It could be a lookup table coming from a known profile. It could be a combination of linear, nonlinear functions that define the path or the profile that the particular machine needs to perform. In this case, we keep the height, but make the time that it requires to reach there as a parameter, and the smoothness of that profile also a parameter. Of course, as I mentioned, this could have been an equation. So I have now added 3 parameters to the system. I'll define them in a parameter block. This, depending on the type of physical properties that we are dealing with, can be added units here. We'll just leave it at real for now. So I have a model that is parameterized with the features that I am interested in, namely my profile and my external forces. What I'm interested in is what is the torque requirement. One way to explore the model a little bit further is to use MapleSim2 Connectivity and start interacting with the MapleSim underlying equations through Maple. So there are a variety of templates available to users. Some of it are add-ons for specific tasks such as code generation to Simulink or other platforms such as FMI. But there are some that come with the basic MapleSim, one of which is a blank worksheet that will allow you to create your own applications and design tools or design and analysis tools. So let me zoom in so it becomes better viewable. So the first line that is already put in there is to establish the link between the Maple session and the MapleSim model that we were just working on. So let's have some basic ask some basic questions. I want to know what were the parameters that are available to me in the MapleSim model. So I issue the get parameters to make sure that the parameters that I want to access are accessible. Here they are F, S, and T. So let's assign them to a name because we will use them later. So now I have a list that is parameters F, S, and T. Now I use the command from MapleSim package called getCompiledProc, and what it does, it generates the equation and creates C code and compiles them, and basically what I end up with is a function that I can call over and over again, and it benefits from the symbolic optimization of the equations and code generation. So it is something that basically the underlying function for our multi-column analysis, for our parameter sweep, and also all sort of optimization. Here we kind of going to use it directly. So let's first build it. I'm going to call it cproc, and I am using the getCompiledProc. I'm going to leave there a variety of options. You can override the graphical user interface setting on solvers, number of data points, and all that here, but I'm going to leave everything except I am going to give it the requirement for the parameters that I want to investigate, which are the variable we just set to PRMS, and I'll just pass it along and create the compiled procedure. Depending on the model size, this will take a bit of time. In this case, it's quite fast. So now I have a procedure that I can call. Let's just give it a try. I am gonna run the model with a set of parameters. Select, and the order is the order that I have defined it with, which is F, S, and T. So let's say 100 newtons, not so smooth trajectory, and rise time of 2 seconds. I'll get the results back. So I have 3 results. I can also ask the CompiledProc to tell me what are the outputs. Let's just do that. So there are 2 outputs. First one is phi and tau, which are taken from the probe that I added to the model. Of course, you can directly add any variable accessible from your model to the list here. We didn't do that. We used just the defaults, which will be the probes manually added to the model. I'm interested in torque, so I can just plot it. The first is time, and the ones that we saw on the list will be the second and third. So I'll plot time versus the torque. So this is the plot of torque over 10 seconds. Now this is great, but what I want to do is I want to get a sense of how system behaves as these parameters change. So I want to be able to explore it in a more automated way. For that, I'll need to put these steps of running the model and plotting it into a procedure. Then I will be able to easily explore that aspect of my model, which is the plot of torque versus time. So let's just do that. I am going to define a new procedure. This procedure will get force, time to, let's just use the same order so that we don't make mistakes. Not necessary, but the smoothness and the time, the rise time of the profile reaching the 1 radian rotation. So I'll have that. Locally, I'm going to need a variable called res, so I'll have that too. Now I'm going to define res just as I did here by calling the cproc, except this time I'm going to pass to my procedure the arguments of this wrapping procedure. Rams equals f, s, and t. Okay, now I need to do the plot, which I will do by stealing this line. There we go, and I am done. So now I have a proc or procedure that not only runs the model, plots the model as well. Let's give that a try as well. So I'm just going to issue plotter, and let's pass to it the same numbers as we did the other time, and we get the same plot. So this is great. This is this automate part of it. I can keep passing parameters. I can use Maple programming language to pass a variety of lists of numbers in groups and plot them on top of each other. But I want to, for this presentation, I want to do a little bit of an automated way of doing that, and that is to use the explore command. So I pass the plotter, the function that we just created, to it, f, s, and t, and parameters. Now I need to give a range for my parameters. So let's say we say that the force starts from 0 and goes all the way to 100. The rise time starts from 1 second to 2 seconds. 2 seconds. And the smoothness will be from 0.1 to 1. Okay, I have that. Now, explore command creates automatically an interface where I can change the model, have under the hood the compiled procedure that represent my dynamic model run, and get a sense of how things change. So let's explore the model. So if I increase the time, you can notice that the maximum or the peak torque that the motor is required from is decreases. As I decrease the time or speed requirement or acceleration requirement, I would require more torque from the system. Similarly, if I make the path smoother, I will need less torque over a larger time, and I can add more options to this to calculate the total power or total energy required by the motor as well. However, in this particular model where the inertias are small and the acceleration is not too great, the dominating force could quickly be the external force. As I increase the external force, basically it will dwarf the requirement by the just by looking at the inertial forces. But depending on the type of application that we are looking at, it's important to know there are regions of operations, one dominated by the acceleration and inertial forces, and one dominated by the external forces. And potentially, depending on the case, there could be cases that both effects, as we see here, would come into play side by side. So that was an application of having a MapleSim model that starts from a CAD representation and ends with a simulation in Maple. As I mentioned, I encourage you to have a look at the models that we have in our model gallery, where we focus on other sides of modeling, such as the model that starts with a CAD but then incorporates hydraulic systems. We have models that start with a CAD, but the actuation is added to it via an electrical motor and battery for the source of the energy. Hopefully this short presentation gave you some idea of the kind of things that you can achieve with this new addition to MapleSim, which we are very excited about, and this presentation has been helpful to you. Thank you very much.